Uh, I mean, a lot of those corrections come about because in the sense of gravitational back action type stuff, and the fluid back actions are very different from the gravitational ones. So, it's quite possible that they might exist, but they wouldn't be in any way similar to the gravitational ones is my suspicion, but that's based on more or less nothing.
But sorry, all of these corrections on low energy curves depend on stuff happening at very high energy. So that's why I'm asking the question.
Right. I'll have to leave it at I don't know.
Wait a second.
Yeah.
I want to ask you other question. Yeah. You see, because...
Why don't you go there, because otherwise it's too much.
No, but then we'll have a musical chairs if we do that.
Musical chair. Okay, so do I need... Look,
You can have musical chairs.
you see, if you would assume...
You're putting me on the spot here.
Yeah. Now you can hear me, right? Okay, good. So, could you check the following thing? If, for instance, we are assuming that the area of black hole is quantized in units of the Planck unit, then black hole cannot emit quanta of radiation, Hawking radiation, with a scale larger than the size of the black hole, right? Now, when you are making this analogous gravity experiment, maybe you can check this thing, because, also it's hard to imagine that some analog of black hole can emit the quanta with the size which is larger than the size of typical system. Or you are doing mostly one-dimensional stuff.
Well, in these analogs, the wavelength is more or less sort of like the surface gravity, but there it depends on exactly what the rate of change of the fluid flow in, and that's you can sculpt that. You can make that anything you want for a given size of dumb hole, as I call them, things that can't speak.
So in principle, it's possible.
So you can
because you understand that if you would take, for instance,
I mean, certainly the wavelength and the size of the system are related again in the analogs, just as they are for the black hole.
Right, but I'm asking
it's just
now.
In the black hole,
right.
that's also related to the mass and therefore the radius, whereas in the fluid system, it can be anything you want.
You think that could be anything? For instance, if I will take electromagnetism, which is, for instance, in some ball with the appropriate boundary condition, everything can be thermalized, but nevertheless, you know that when we open the things, we are getting definite frequencies, and there are no frequencies which would correspond to the wavelengths which are larger than the size of this resonator. You see, if you take just electromagnetic radiation, put it in some box with the appropriate boundary conditions, then spectra can be perfectly thermal with all high correlators, but nevertheless, instead of getting continuous Planckian curve, you are getting curve which consists of lines. We were checking it together with Jacob Bekenstein, yeah? So we checked all high correlators. If the system has finite size, then it's not continuous Planckian spectrum, and it's significantly damaged, for instance, in this Rayleigh Jeans spot.
I mean, a lot of those arguments depend on the, that Einstein's theory is what is the back you get the back reaction kind of stuff, and here the back reaction is so different.
Here the back reaction is so different, but it could be, for instance, one of the predictions of non-perturbative quantum gravity.
Right.
In case if we would find really, exploding primordial black hole, like quantization of the area in terms of Planck area, because anyway we cannot measure the areas which are smaller than the Planckian area.
Right,
right?
I mean, here
I
the
don't know how
Planck
to do
scale
it.
sort of corresponds to the interatomic separation of the atoms and so forth,
Yes, this
which
I
is a-
no, here,
which is a
yes.
very different kind of
This is also
structure
showing
than it would be in general relativity. So I think, if I understand what you're asking, I think it's outside the purview of what these analog experiments can really tell you, but I'm not sure.
Just to comment in response to what Slava was saying, there's an often underappreciated fact that the wavelength of Hawking radiation isn't the size of the black hole. It's at least 10 times bigger or something like that because of factors of 2 or 4 or whatever pi. So, yeah, but it's at least an order of magnitude. So there isn't a true limitation from the size of the system.
Right, but if you could take, for instance, this Planckian spectra, right, then there is a whole range which is called Rayleigh-Jeans range, okay, which would be absent in this sense when you would be making measurements. For instance, okay, the wavelengths which are 20 times larger than the size of the black holes would be suppressed just. They would be absent.
There is a suppression, but
Suppressed, but not exponentially. How to call it? It's not linear power like the Planckian spectrum. You see? Because also when we were estimating them, there was clear prediction that instead of continuous curve, you have the curve, not curve, but a lot of lines, each has 3% width of the distance between the lines, and the envelope is okay, like Planckian spectrum. So it would be clear indication in case if experiment would be possible.
Okay, let's go on to the next topic because I think this has been discussed.
Yes, I would like to ask a question which in some way relates to what Phil and Slava were talking about, which is, of course, well, the analog in the analog system. So this has been, as you have, again told us today, beautiful physics has come out of studying these analog systems. Now, I'm, of course, a theoretician. In the best of all worlds, I'd love to learn about quantum gravity from analog systems. But then, of course, this notion of analogy is just very elastic, let's say. So it doesn't help me particularly unless we make it more specific. And there are, of course, examples in physics precisely where you have vastly different systems microscopically exhibit common behaviors which, say near criticality, as we know from statistical systems, is expressed in certain exponents, critical exponents, and these are exact numbers. So to the extent are there such more stringent examples of analogies, like predictions of an exponent that, I could be measuring whatever, using lasers or something else, that would say, look for the same thing, in your non-perturbative quantum gravity, whatever, and you would find the same exponent.
I certainly don't know it. My feeling always is that the analogy is good for some things, and once you start getting into, the real gravity part of it, most of these analogies, I think, just fail. What's amazing is how much they tell you about the quantum mechanics in a background space-time. But once that background space-time becomes a quantum space-time, then I think you're in the regime where these analogies really, I don't trust them at all. Now, it may be that there are certain analogies which would be a much better analogy to, quantum field theory
Well, we are really
and a
talking
quantum
exactly.
space-time.
Yeah. About universal, we're thinking of universal, relations, properties,
Right.
laws even.
But yeah, and I don't know. I haven't really thought deeply about that, so I don't have it, and my first reaction would be that I don't believe that they exist, so I don't spend very much time searching in places where I don't think I'm going to find something, which is always dangerous, of course, because that's where you often find surprises. Bob.
Yeah, no, I had a question I was going to ask Philip at the end of his talk, which is kind of a follow-up on John Donahue's, although I was going to ask this anyway, which is presumably one could formulate a correlated world line theory in electrodynamics, I mean, which I guess would then differ from standard electrodynamics primarily in that the charge, an individual single charge particle would interact with itself, or its different paths would interact with itself. So I guess the question is, can one do such a thing? And if so, how would its predictions differ from standard quantum electrodynamics? I mean, I'm not saying one would want to do that as a new theory, but just that would help understand how the differences in the correlated world line theory, how that differs from standard quantum field theory like quantum electrodynamics.
Let me answer that specific question first. I think you can see that if you had those kinds of interaction between the different paths of a single electron, then the world would look very, very, very different from what it does now. You'd have an enormously powerful repulsive force between the different paths for a single electron. I don't think an electron as we currently know it would exist. In other words, the theory would be completely pathological. I mean, I haven't tried to think about what would happen in all the other various theories that we have, but I think you would find the same thing, that it would look utterly different from what we observe. I remember being asked by a referee to do with one of these papers, how small would the electromagnetic coupling have to be for this to still work? And my response was, I don't remember the number, but it was ridiculously small. Something like 10 to the minus 86 of the current coupling. But so that's the answer to your specific question. Now, we were having a discussion in the break about the thought experiment that I was running, and I have to confess that I'm going to have to think this one through in quite some detail. And I'm reminded of the remark that thought experiments are very dangerous. One of the most famous thought experiments that we know, Einstein's elevator thought experiment, is just basically completely wrong, as it was first pointed out by Singh. I remember being convinced of how wrong it was when I realized that if you take a droplet of fluid which has no surface tension, then its shape is distorted by tidal forces no matter how small it is, which just shows that the elevator argument is just completely incorrect. And I've often wondered because I don't think anybody pointed this out in print that it was just completely wrong until after he died. But I just wonder how he would have reacted when it was pointed out to him that it was completely wrong. And I suspect he would have said, who cares? Just look at the theory and see what it predicts. So I will have to think through this analogy better. But it is certainly the case that if you tried to do correlated world lines for any other theory than quantized gravity, you would get total nonsense. I mean, not only would it not correspond to what we observe, but the theory would just be completely pathological.
I think we are running out of time, and there are a couple of questions. So
Okay, can I? It's for you.
Sorry, and in a certain sense, all these arguments that I went through with Andrei Barvinsky were designed to show that you do get a consistent theory if you include the correlated world line interactions. It would be very interesting to go through the same exercise with QED. I suspect we would find that it wasn't consistent.
Yeah, I just had a few basic questions because I haven't been exposed to too much of the theory. So you made various statements about, I mean, you put it on a par with, it's not just string theory, but here's another consistent theory of quantum gravity. Did I understand that right? So So this is, and you also said it's a quantum field theory, so I assume of dynamical gravity, and what, particles, or is it local fields of particles, or is it world lines? So is there a kind of a non-local aspect to this?
So I didn't get a chance to show all those technical slides, but
I tried to.
essentially the action that Andrea and I were dealing with most of the time was a scalar field coupled to gravity.
Okay, so you have just standard perturbative gravity in that sense.
Well, but all of the general discussion was not perturbative. Calculations that we've done have been perturbative, but the general arguments to do with consistency and so forth were not perturbative.
But I don't
So you
know- I
write
mean,
down,
yeah.
for the, supposing we start off with a Gibbons-Hawking form for the action for quantum gravity, okay? For a scalar field, including all the bells and whistles, you know, the Faddeev-Popov ghost fields and so forth. And we now make the crucial step of not just summing over, of course, when we're dealing a field, we don't, when we say, I think Jim Hartle used to get so frustrated by the word path that he started talking about histories. So that to make it clear that we were talking about fields, not particles. Okay, so we now in CWL introduce the idea that we sum over all possible histories in this path integral, whether it be a path integral for some generating function or for a transition amplitude, but now we allow the gravitational field to interact between the different histories.
Yeah. I'm really interested kind of in the gravity part of the story, right?
Yes.
So, and that is just what, standard perturbative gravity? I don't understand in what
It's
sense
the standard.
it exists.
It's the standard action
Yeah.
with, you know, the York-Gibbons-Hawking terms added,
So you
depending on
just
what
have
kind of a manifold
path
you have.
integral over G mu nu.
Yeah, exactly.
So, but that's a standard, you know.
Well, but it's not perturbative.
But in what sense is it not perturbative?
There's no measure. You don't specify that measure in a non-perturbative sense. That's the question.
Well, sorry.
In what sense you're writing down the path integral? In what
so
sense
you're
does this?
asking about the measure up to scales of the Planck energy.
I'm asking about the path, just the fundamental quantity you're writing
Right,
down. But
so-
is a path integral?
So let me
over G mu nu?
clarify that there is no attempt to treat this path integral up to energy scales or down to length scales of order the
Okay,
Planck
so
length.
it's
So it's an
perturbative-
effective low energy theory.
Okay, it's a
Yeah.
perturbative path integral with respect to the gravity.
But it's not
Part.
perturbative in the gravitational coupling. I don't know what you mean when you say it's perturbative.
I mean, weak fields.
No. It's low energy, but not weak field.
So in what sense does then the path integral exist?
Sorry, are you saying that you believe the gravitational path integral only for weak fields?
What? No. No, but we know that that is very difficult to do it
Yeah,
beyond
remember that
perturbation theory.
this is an effective low energy theory, so we're not allowing, for example, transitions between different topologies, which would be allowed in a general path
No,
integral.
I'm not talking about this. I think we should talk in private about this. Yeah.
I mean, if we had more time, this is a very interesting topic, but I think since there's one last question and we are already over time, do you want to ask a question, Steve?
I think this is somewhat related. So the notion of summing over world lines is very much a first quantized point of view. And in field theory, we go over to a second quantized perspective where we say sum over field configurations. That's what you were just touching on. Now, the path integral there, you can think of as, one way of describing it, it's the solution to a problem. You want to solve, say, the analog of Schrodinger's equation for fields with a certain Hamiltonian and so on. If you think about it from that perspective, what's different about your formalism? Is it something that is now going to be non-local or non-linear, or what? If we don't think about it just from the point of view of path integrals, but from, say, the point of view of evolving wave functions, what's the essential modification here?
So I have to say that from the very outset, I prefer not to think in terms of wave functions or Hamiltonians. So we're very much adopting a covariant approach here. And one of the reasons for that, although it wasn't an initial reason, but for me it was a very important reason, was the discovery of papers by Jim Hartle, in which he discussed how one does quantum gravity in the presence of achronal regions of space-time, and he pointed out you simply can't formulate this in a Hamiltonian framework. So for me, that was how shall I say it? It improved my faith in the covariant formulation.
Well, but one may not be forced to think about such region. You know, that's sort of an interesting mathematical case, but, you know,
Well, I
in a
don't
lot
think
of
it's,
familiar...
I'm sorry, I disagree. The simple fact is that we have achronal regions in the universe. We've got black holes everywhere, Kerr black holes, so we should be worrying about this. Well, actually, I think we'll be hearing about that on Wednesday from Kip. But, I mean, I think his point of view is the opposite of that. But in any case, to answer your question about the formalism, it is, so we're avoiding Hamiltonians. And the idea is that the primitive element in the theory is not a wave function, but a path or a history. Okay, and if you like, the assumption here is that what differentiates it from conventional quantum gravity is that the histories are coupled.
So Philip, will you be doing predictions on your theory and to design some experiment and give us a preview of what the experiment will look like?
Well, that is work in progress.
No preview?
I'll leave that up to, we'll see.
Just to close up, say, this whole discussion up here. So, I mean, there's a difference between actually evolving a wave function using Hamiltonian or something and having a Hilbert space and kinematic description. If you don't have the Hilbert space or kinematic description, I don't know what transition amplitudes are supposed to mean, for example, normally. So do you have a Hilbert space in the kinematical level, and you are implementing dynamics in terms of this
Right.
correlated part?
So again, I referred to Kibble in my talk, who came to the conclusion in his work in 1979 that one simply had to drop the idea of basing everything on a Hilbert space.
Okay.
So the question is, the question you're asking me is essentially, okay, so what are these paths or histories?
No, what are the amplitudes, final amplitudes that you actually
What do they-
calculate?
what-
What is the meaning of them?
Right.
Why do you call them probability amplitude if in fact there is not an inner product or anything like that?
Yeah, well, I actually don't call them probability
Okay,
amplitudes.
so what do you call them? So what is the physics? What is the physical quantity you actually
So
calculating?
the argument here is that the only consistent theory is where you stop basing everything on measurements and probabilities for measurements, and everything has to be treated quantum mechanically.
Yeah, but that's quantum mechanics, probability and
Well,
measurements.
no, but with the added ingredient that I mentioned. Okay. But if you insist on talking about probabilities, then you have to introduce, in the same way that we do in ordinary life, you have to introduce a notion of probability for situations in which you don't have complete information.